Good night. Once again, yours truly, Dolphy Alexander Gilpin. I'm coming to you from Decatur, Georgia, 1534 LaVista Drive, Decatur, Georgia, United States of America. And tonight I am continuing with my CME, and particularly we are on ECG, electrocardiogram, sometimes referred to as EKG from the German perspective. EKG, German perspective, and the ECG, the British and the American and worldwide perspective. Now, a background history of my personal study with EKG. In 1982, I did my first professional course in electrocardiogram, which also was integrated with electroretinogram and electroencephalogram and other diagnostic means, X-rays, computer-aided tomography, CAT scan, and ultrasound. Now, this was a course, a combined course, engineering and nursing course, HCT 321, Healthcare Science Technology 321, taught by Dr. Pennington and a professional engineer at the time at City College in about 1982. So this was my first professional course in ECG or electrocardiogram. That is City College of the City University of New York. Prior to that, I had intermittent relationship in other courses when it was briefly introduced, ECG and other electro-diagnostic means. And after my course in City College, I continue with the theoretical aspect of this ECG in Schilling's laboratory, master's PhD laboratory. And there I was of particular interest in this ECG and other electro-diagnostic means because of the electrical properties, the electrical property that is characteristic of the ECG. As an electrical engineer, anything that had electricity coming through it or going through it or that had some relationship with electricity was of interest to me at the time as an electrical engineer then. Well, let me say the ECG 321 Healthcare Technology course not only was subjected to CCNY, the course was continued over at Mount Sinai Hospital in New York, whereby after the theoretical aspect of the ECG was started, CCNY, the student that was to go over, including me at that time and other students, to Mount Sinai Hospital to see the practical application of this ECG and computer tomography and ERG and other electrodiagnostic means. So it was a joint course, CCNY and Mount Sinai Hospital course at the time. I know tonight I am, that was just a brief background on my ECG. Also in 1990 to 1996, during my specialized medical research, ECG was also used, but it was merely implicit at the time or remained dominant. Other aspects of medicine was at the forefront, like the study of cardiology, pathology, pharmacology, and ophthalmology. They came to the forefront, and the diagnostic means was a little bit suppressed then. Nevertheless, here we are. We are on ECG, and we say now that normal sinus rhythm, the rate is between now 60 and 100 beats per minute. And greater than 60 to 100 beats per minute, we have a thing called tachycardia. And less than 60 to 100 beats per minute, we have bradycardia. There are some wave, a sort of expansive PQRS wave for the ECG or EKG. And first we have now the P wave here. Let us use a sort of a thing. The PQRS, the P wave. Let's get this thing here. And right now the P wave, Q down here, R, S, T, and sometimes a U wave, which is after the T wave. The U wave is sometimes so small that it's negligent in most PQRST representation, but it is there and it is not known, well known of the particular source of it, but some medical scientists say it's the repolarization of the Purkinje fibers that cause this U wave. Nevertheless, you have the PQRST wave, and as you know, the ECG represents the electrical activity of the heart. I will come to show it more clearly in a little moment. In this little diagram here, we have the P wave with the PR segment. If this is the P wave, the PR segment start from here to here, and this is the Q. That's the R, S, and we have this as a ST elevation. Notice in comparison to this one, this part of it is sort of depressed relative to this one, which is elevated. We call this the ST elevation, and particularly this ST elevation called STMI STEMI is a representation of myocardial infarction. ST elevation, myocardial infarction, STEM 1. Nevertheless, here we have now the R interval, the PR interval starting from here to here, the PR interval, and the ST interval starting from here to here. And as we say, this is an ST elevation. As we come over to this one, which is really more representation of a normal ECG here, on the right side here, we have normal QRS is within less than 3 small boxes on the ECG paper. And on the ECG paper, 1 small box represents 1 millimeter. Therefore, 3 small boxes will represent 3 millimeter. And usually a normal PQRX complex fall within 3 millimeters or 3 small boxes. Now, normal PR interval is within 1 large box, and 1 large box not shown here, we'll show you in a moment on the reverse side, consists of about 5 millimeters or 5 small squares making up 1 large square, or 5 length and 5 breadth. We'll come to show the vertical representing some millivolts and the horizontal in millimeter representing we have 3 units there, volts, time, and distance. We'll show you that more explicitly on the reverse side. So normal PR interval is within about 1 large box, and the PR interval of 0.11 to 0.20 seconds. The QT interval normal limits is 0.40 seconds, which is greater and greater than 0.42 seconds represent prolonged interval. That is greater than 2 large boxes. And 2 large boxes would represent about 10 millimeters. Now the QRS normal size is 0.06 to about 0.11 seconds. And 0.12 seconds represent ventricular depolarization. So those are just some introductory notes on our electrocardiogram. In this one, in comparison to this one, we have a ST elevation, we have a ST depression, with the S wave being in a depressed here, and the T wave called the ST depression. And remember, there's a U wave that is sometimes negligible, it's so small, it's not seen. Okay, let's move on to some more representation of our ECG on the reverse side here. And here once again we have a normal ECG, electrocardiogram, with our P wave, Q, R, S, we call this the PQRS, the QRS complex, and the T wave, and the U wave. And over here we note that the P wave is represented by this first art diagram here, a very simplified art diagram, and it represents the atrial contraction. Atrial contraction, here's the two, the right atrium and the left atrium. The right atrium is on my left hand side, really, here, and it represents the atrial contraction, that is the P wave. This is a normal representation. The QRX complex represents contraction of the ventricles, the QRS complex, and it is shown in this diagram here of the heart, a simplified diagram of the heart, contraction of the ventricles. And the T wave represents a recovery wave, which is the relaxation of the ventricles, the T wave, the relaxation of the ventricles. So we have now the P wave representing atrial contraction, the QRS wave representing ventricular contraction, and the T wave representing recovery wave, ventricular polarization or ventricular relaxation. And as we said, the U wave, which is sometimes not shown, representing the Purkinje fibrase. It's a source from this, not well known, and it's sometimes left out of the PQRST. But here's a U wave coming after the T wave. Now, I've drawn a simplified diagram of the heart here with 4 valves, and this is the tricuspid valve here, the mitral valve there, but it's more complex than that. This is a simplified diagram. However, the tricuspid valve, the mitral valve, the aortic valves, or semilunar valve, the aortic semilunar valve, the pulmonary semilunar valves. So there are many more valves that is involved in this blood coming from the atrium to the ventricles. But here we have just shown the tricuspid and the bicuspid mitral valves. Here we have tried to show now more diagrammatic with the boxes representing a normal wave here. And we say one small box represents 40 milliseconds, which is 1 millimeter, and 5 box represent one large box, represent 200, that is 5 times 40 milliseconds, 200 milliseconds. And one small box representing 0.04 of a second, which is equal to 40 milliseconds. And 5 small box representing 0.20 second, which is represent 200 milliseconds. On the vertical scale here now, what we have is 0.5 millivolts representing 5 millimeters. That means 10 millimeters will represent 1 millivolts. 0.5 millivolts on the vertical scale representing 0.5 millimeters, which is 5 small box on the ECG page, and therefore 10 small box will represent 1 millivolts. And here we have a representation now of the normal PQRS, normal PQRS, and the boxes are expanded here because 1 millimeters is much smaller than this, but you have drawn an expanded version of it. Even the PQRS T waveform is also expanded here, and to show 25 millimeters equal 1000 milliseconds, which is equal to 1 second. So that's in this diagram here, and this is a normal representation showing the PR segment and the PR interval. The QRS interval, which is from here to here, the QRS interval, and the QT interval, which is from here to here, the QT interval, and the ST interval from here to here. We also come up with some small, let me try to highlight this here now. That is if my ECG readout representing ventricular fibrillation. Let's try to see if we could highlight it a little bit more here. Ventricular fibrillation. Yeah, that's the first one, representing ventricular fibrillation. The second here representing now ventricular tachycardia. Yeah. Try to make the waves more explicit here. So this one representing ventricular fibrillation, and this one representing ventricular tachycardia, and the last one here, just almost horizontal line here, representing a systole. Remember now, one small square is 1 millimeter, and 5 small square representing 1 large square would be like 5 millimeters, and the scale is now 0.5 millivolts equal 5 millimeters, and on the vertical scale now we have a voltage 0.5 millimeter representing 0.5 millivolts, or therefore 10 millimeters representing 1 millivolts. With respect to our AMZ 5 cos matrix, we know that already our ECG was in a sort of medical abbreviated representation, ECG, and there was no need to fabricate or synthesize any abbreviation for it. It has been well known that ECG stands for electrocardiogram, and therefore all that is necessary now is to attach 8 magnitude numbers to it to get it in our 5 cos 12 configuration. And therefore we could use some small number now in microvolts, which would have about 6 to 8 figure representation, or millivolts and volts, and also seconds, microseconds, and in distance now, millimeters, very small numbers, nanometers, millimeters, micrometers, and so on. And that would give us our ECG in the 5 cos 12 configuration, representing